Hello, so this is a breakdown of chemistry, higher tier, triple chemistry paper 1, May 2023. So the point of this is, just like any of the other paper breakdowns, if you've ever seen any of the other ones, is breaking down my thought process behind answering the questions, how you get to the answer, and then obviously giving the answer. So here we go. So question 1 is about the history of the atom. So this is your one where you should know your timeline, Democritus, your John Dalton, your J.J. Thomson, all that stuff. So atoms originally thought to be tiny spheres, could not be divided. That was tiny spheres was Dalton, and then obviously cannot be divided was Democritus. Plum pudding model of the atom was then developed, which was good old J.J. Thomson. So here's your picture, plum pudding model. Describe the plum pudding model. So you just look at the picture and use the picture to help you answer this question. So the first thing you can say is, how do we describe this? Let's go for the plus part first. The first thing we can say is it's got a ball of positive charge. Right, positive, negative, you're always looking for the word charge. And then the second thing, there's a few ways you could say this, but you've just got to think about what are these negative signs supposed to be? They are electrons. So the way you can say this is you can say negative electrons embedded. You could say like embedded throughout the structure. You could say scattered on the surface. You could say scattered throughout, etc. Just some reference of it being a ball of a positive charge and then there being negative electrons all over the place. We'll get you the mark. Atoms contain electrons, neutrons and protons. Write these three particles in order of their discovery. This one can be a little bit tricky, even though it's an easy question, because you're thinking about the order. So the first one you should be able to remember is neutrons were the last ones to be discovered. Right at the end, the particle that they knew existed but couldn't prove it, so James Chadwick came along and proved it later on. So then the idea of protons, that only became a thing when the idea of the nucleus of the atom was relevant, so needed to be referencing a nucleus at that point, which is Ernest Rutherford's whole spiel. And then earlier than that was the J.J. Thomson model, and we're talking about negative electrons on the surface. So the earliest one was electrons, the second one was protons, and then the latest one was neutrons. This question is talking about tennessine. Very few atoms of the element have ever been identified. This is the atomic number, which is kind of irrelevant for this question. Predict the number of outer shell electrons of an atom of tennessine. As soon as it says outer shell electrons, I am thinking group. Give one reason for your answer and use the periodic tables. You got your periodic table sheet. Number of outer shell electrons is always whatever group it's in. This is year 7 stuff. So 7 electrons on the outer shell because it's in group 7. Simple. Tennessine was first identified by a small group of scientists in 2010. Suggests one reason why it was not accepted as a new element by other scientists until 2015. Just like anything in science, just because one person did it one time doesn't necessarily mean that it's true. It needs to be confirmed and it needs to be tested by other scientists to prove that there were no mistakes, that they're not just lying and trying to claim credibility, etc. So it needed to be put under peer review. So this question is talking about isotopes, which explain why some relative masses are not always whole numbers. Element R has 2 isotopes, and this table shows us the percent abundance of the isotopes. Calculate the relative mass of this unknown element R. Give your answer to one decimal place. As soon as you spot that, I would get into the habit of underlining it, highlighting it, because that's going to be where one of these 3 marks comes from. So you might get the answer and then you don't do that bit and you miss a mark. So for this, the way we would do it is we're going to do, it's a bit like calculating a mean almost. So you're going to do the mass of whatever isotope 1 is times the percentage, and then add that to the mass of isotope 2 times the percentage, and then divide by 100, because that's the total number of percentages we've added together. So all we're going to do for this one is mass 1 is 6, mass number 6 times 7.6% plus the mass of the other one, which is 7, times the percentage, which is 92.4, divided by 100. If you struggle with calculator stuff, you can even do this bit equals first to get your answer, and then divide what you get by 100, or you can just put it all in like that, and then you will get a final answer of 6.924. Now, that's not all the marks, because if you remember what we said before, you need to put it to one decimal place. So you just pick the first two numbers, first decimal place, everything else gets rounded. It's a 2, so it rounds down. So the answer is 6.9. Just very important, significant figures, decimal places, etc. Make sure you note that down the moment you see it, because chances are when you get into the flow of starting to answer the question, you just go, oh, great, I've answered the question, and move on without thinking about the fact that you need to get it to that. So if you spot it, underline it, highlight it, so you don't forget those important bits. This question is about temperature change. Since your polystyrene cup required practical, which you should be very familiar with because you should have talked about it many times. It always comes up on chemistry paper. It investigated the change in temperature of a solution when different masses of ammonium nitrate were dissolved in water. There's the method. You've read it. You can read. The independent variable and the dependent variable in the investigation is what we're trying to find out. Remember, don't mess in class. Dependent, you measure. Independent, you change. Right? So we'll do independent first. What are we changing in this? The key word for change is repeat with different. That's usually what the independent the form that it comes in. It says with different masses of ammonium nitrate. So that's our independent. And then for the dependent is what we are measuring. So clue is there, investigate the temperature. Usually it comes, normally in methods, it gives you the highlight of what both of them are in the first sentence. They investigated how this affected this. That's usually telling you both of them. So you can also check it in the method if you're reading it. What are they trying to work out? They are measuring the lowest temperature reached by the solution. With this one, you could think about this measuring the temperature of the water, because we're trying to keep the water the same temperature to start with to make it fair. You can either put for this one the temperature of the solution, the lowest temperature of solution. You could put temperature change, but that's allowed. But it's mainly this one, is what we are measuring. So here we have a graph question, so you should be rubbing your hands together for the easy marks that you're about to receive. It says plot the data from table 2 on figure 2, draw a line of best fit. So remember, these points here tell you where the marks are going to come from. 3 marks for doing that, so it's probably going to be 2 for the plotting and then 1 for the line of best fit. Here's our table that we're using the data for. We're going to figure out what the scale is to start off with. So on our x-axis, and our y-axis. On the y-axis we've got from 10 to 12 there are 10 little jumps, so that means each little tiny square is worth 0.2, and then from 0 to 5 we've got 10 jumps, so that means each little square is 0.5. So we'll start off, so we go along the corridor, up the stairs. I'm going to go along to 4 for the mass, and I'm going to go up to 18.2. You use a pencil for this. You do it faint first, and then when you're 100% sure, you can go over it a bit harder. Make sure you do it hard enough so that your examiner can see it, because time and time again you see it where people do it so faint it doesn't even look like a plot. But do it faint to start with. So then we go along to 8, which is there, and then up to 16.2. Remembering that as you do this, you've got to be as precise as you possibly can, because go along to 12, you're only allowed half a small square out before it becomes wrong. 15.2, go along to 16, to 30, up to 13.6, so I know 13 is there, so I'm going to go 13.2, 4, 6, 20, up to 12.4, and then 25, 24, up to 10.6. Right, that's this bit done. Then we're going to draw a line of best fit. Remember, when you draw a line of best fit in science, you follow whatever the trend says on the graph. If it looks like a curve, you curve it. If it does a down curve, you curve it. trying to go through as many as you can. You don't do dot to dot, never do dot to dot. If it looks like it's going to be a straight line like this, you do a straight line. You're going to use a ruler, and you're going to make sure if you've got plots scattered like that, you're going to try and make it so that your line goes through the middle of them the best you possibly can. So if they look like they all make a straight line and one is off the trend, follow the trend. You want to make sure that there are the equal amount of points on each side. I'm going to try my best to do this with a ruler, but I am on a tablet, so this is going to be difficult. Yours will be better than this. Okay, that's pretty good. Right. Then next question. So you're going to determine the initial temperature of the water. You should extend your line of best fit. Initial temperature of the water means no ammonium nitrate. It's before we added it. So it's going to be what was the temperature of the water at 0 mass. So we're going to carry our line up with a ruler. I'm going to do it without freehand, but you do it with a ruler up like that till you get to your y-axis, and then you determine, so you'll get one mark for doing that straight line, carrying it on, which is easy enough, and then 1 mark for looking here to wherever your line goes across. So mine right now goes at 19.6. right? That's last mark for that one you get for whatever your line goes through the y-axis at. That's what you get the mark for. So if you did a rubbish line and you did it there, but you read this number correct, which is 17, you would still get that mark. How do the results show that dissolving ammonium nitrate in water is endothermic? Endothermic, we're talking about energy. It says endo, so we're talking about energy entering the reaction. When the energy is entering the reaction, that's absorbed from the surroundings. We feel that as cold. How do we know that it's endothermic? It's because the temperature decreased. You can't talk about energy transfer, energy going into the reaction, etc., because it says how do the results show, and the results are only talking about temperature and mass, so you don't talk about energy at all, you just talk about the temperature. So the student repeated the experiment 3 more times. This is the result for 8 grams of ammonium nitrate. So they've done trial 1, 2, 3, 4 and calculated the mean, and then recorded the mean lowest temperature is 16.5 plus or minus 0.3 degrees Celsius. Explain why they included that after the mean lowest temperature. So the first mark is coming from what is that? That means so plus minus 0.3 degrees Celsius is uncertainty. So when we are doing this, to work out the uncertainty, all you need to do is it's either you can do half of the range, or it's the range around the mean. So if we do that up here, so the mean is 16.5, going up to the biggest number is 16.8, so that's plus 0.3, and then if we go down to the smallest one, which is 16.2, that's down 0.3. So that's all the uncertainty is, the range from the mean. So looking at the same data, what type of error is shown in table 3? So remember, 0 error is when it won't go to 0, so you can't get your mass balance or whatever it is that you're measuring to 0. That would mean that the reading would be the same, wrong by the same amount each time, which it's not. Systematic error is something faulty with the equipment, and then the random error one is the one where we're talking about subtle variations to do with human misreading it or mistakes made during the practical, timing of things, etc. So it is random error. So this question is about making a soluble salt. Straight away it says that. I'm thinking about the making salts required practical. which is the one that's all about adding things in excess, then filter it, then do crystallization. It's that whole method. Plan a method to make pure dry crystals of zinc chloride from zinc carbonate and an acid. So we've got 6 possible marks here. The first thing I would think about is, what is this dilute acid that they've not named? So the first thing you can add is, you're going to use zinc carbonate and hydrochloric acid, because it's zinc chloride that it's forming. Okay. Then we're going to add, so first off we can get a mark for saying add the zinc carbonate to the acid. Right. In a beaker, you can specify, make it accurate, stir it. Then we're going to continue adding until it's in excess, until zinc carbonate is in excess. Okay, 3 marks so far. Then we need to get rid of the excess, because if you keep adding it in excess, you'll see that there's leftover solid. So then we're going to filter out the excess. Filter out excess zinc carbonate. Okay, then all we need to do is, we're at the crystallization step, so we're going to heat the solution, and then we're going to wait. So you can even say at this point, so you can even say to the crystallization point, or until it starts to boil, using an electric heater if you want to be really specific with it, and then allow solution to cool and crystals to form. Done. And then you can even add on the end, pat dry with filter paper, or with paper will do. So it's just that method that you've done in class probably a few times. Just specify it. The keywords for this that you need to remember to mention is excess zinc carbonate, then so you're adding it until it's in excess, then you do filtration, and then you evaporate off the liquid to do crystallization, leave behind crystals. Name 2 other substances that can be reacted with dilute acid to make zinc chloride. So a bunch of things that you've talked about that have got zinc in them that will make the variety of different products. First off, you could put just zinc, right? Zinc and hydrochloric acid would make zinc chloride and hydrogen. You could have zinc oxide, right? Because that would end up with, so that one would end up with extra hydrogen, that one would end up with the same salt with water, and then the last one you could have was zinc hydroxide, which would end up with the same salt and water. These 2 are both neutralization reactions. Question 4. This question is about hydrogen and compounds of hydrogen. Figure 3 shows a displayed formula for a reaction between hydrogen and chlorine. So we've got the structural formula for the chemical reaction, and we're talking about bond energy. So the question is on about which expression shows how to calculate the overall energy change for the reaction. So to work out the energy change, delta H, I'm going to put, all we have to do for that is we do however much energy it took to, however much energy needed to be absorbed to break the bonds in the reactants, and we're going to take away however much energy was released making the new bonds in the products. So reactants take products. The way we work out the reactants, so we've got the energy for the HH bond, there's only one of them, so we've got 436, and the energy for the ClCl bond is 346. It's going to be those 2 added together to get the reactants, and we're going to take away the energy from the HCl bond, which is 432. However, there are 2 of them, so we're going to have to times that number by 2. So the answer is the bottom box. The reaction between hydrogen and chlorine is exothermic. As soon as I see that word, I'm thinking energy. So energy is released, energy is exiting the reaction, exothermic. Explain why this reaction releases energy to the surroundings. So remember, whenever you've got a chemical reaction, there's always an endothermic aspect to it and an exothermic. So the endothermic part is the fact that reactants need to absorb energy to break the bonds. However, also, to get the first mark, you also need to say products release energy when the new bonds are made. So that's our first mark. And then why is it exothermic? Well, why is it releasing energy to the surroundings? That means there must be energy left over, so therefore the energy released is greater, is more than the energy absorbed. And that's it. So you just got reactants absorbing energy, products releasing energy, but the products are releasing more energy than the reactants are absorbing to make those new bonds. So this one shows part of a reaction profile. So this is your energy profile diagram between the reaction that's been talked about before. You should label, so complete the reaction profile diagram, and you should do these things. Same as before when we were talking about the graph. To get the 3 marks, it's literally saying this is where you get the marks. So where's the activation energy? Where's the overall energy change? So first off, we need to spot that we said before it's exothermic. It means it's releasing energy to the surroundings. It means it's going to have lost energy in the end. There's going to be less energy in the products than there are in the reactants because it's releasing energy. So we need to complete the diagram. First off, this product line needs to be lower than the reactants line. And then to do the activation energy, you need to make sure you label the point where it starts up to the top of the peak. So that's our activation energy, the amount of energy needed to get the reaction to start. And then we need to, so that's activation energy done, and we need to also label the overall energy change. So that is wherever the energy was, wherever the amount of energy was to start with to wherever it ends up at. So reactants to products, which is energy change. I'm just going to put delta H. Done. So draw a dot cross diagram for a molecule of hydrogen chloride. Hint in the name, hint in the word molecule, and in the fact that it's hydrogen chloride. You should know that these both are non-metals. So we're on about covalent bonding. So therefore, we're not on about the one with brackets and transferring electrons. We're on about the one that involves sharing electrons. So that's the one where you've got the rings interlinking. So the way we start this, we only need to draw the outer shell electrons. So I'm going to draw a circle to put hydrogen in. I'm going to do chlorine a bit bigger because chlorine's a bigger atom. And then we first off, I'll change the colour for this. We think about how many electrons does hydrogen have to start with? 1. How many does chlorine have in its outer shell to start with? 7. Right? How many electrons does each one need to gain to get a full shell? They both need to gain 1. So what they're going to do is they're both going to share 1 pair of electrons. So you start with that in the middle. 1 dot, 1 cross. Doesn't matter which way around it goes. And then when you do the chlorine, you just fill in the rest of the electrons that the chlorine had to start with. It had 7 to start with. However, there's 1 that's going to be used in the middle here. So you're just going to draw whatever's left over. There were 7 to begin with, so there are going to be 6 more on chlorine. Like that. It doesn't matter if they are crosses, as long as there's a cross and a dot in the thing. It doesn't really matter which one represents which element. It's just to show that there's a difference. Figure 5 represents molecules of methane and polyethylene. So polyethene, remember, is a polymer. So that means it's going to be a repeating chain that goes on and on for however many times. Methane is a gas at room temperature, but polyethene is a solid at room temperature. Explain why methane and polyethene exist at different states at room temperature. Now, there's two different things here, so you need to make sure you are comparative in your answer. That means you need to talk about both in your answer. That means you can either say this has this, whereas this has, or you can just mention one and then make sure you use comparative words like, we're going to talk about weak intermolecular forces. Well, you're going to have to say weaker intermolecular forces to make it obvious that you're referencing both. So it doesn't matter which one you focus on. So you can start off with, I'm just going to focus on methane, but you can do the converse for polyethane. So first thing we can say is methane has smaller molecules. Okay, so therefore, because it's got smaller molecules, it's going to have weaker intermolecular forces. Oh, underline the wrong bit. Next up, so we've got 4 possible marks, so we're going to have to make 4 points here. What else could we talk about? We're going to talk about, if we're talking about weak intermolecular forces, we can talk about energy to break it, so less energy to overcome or break. That's the 3rd mark. Where can we get a 4th mark from? Then we can say something to do with why are they different states at room temperature. This is to do with boiling point and melting point. So less energy to overcome, so therefore lower melting and boiling point. Done. You can do it the opposite way. You can say polyethene has larger molecules, so stronger, weaker molecular forces. You get the idea. You can go the other way around. It doesn't matter. It's just as long as you are using comparative words like smaller, weaker. If you just say weak, you're not going to get the mark. 5. Question is about acids and alkalis. As soon as I see that, I think H+, OH-, pH scale, colours, all that jazz. Ethanoic acid is a weak acid. What's meant by a weak acid? It even says answer in terms of ionization. It even gives you the clue of ionization. So how ionized does it become in solution? When it's a weak acid, it means it's only partially ionized in solution. Luckily for this one, it even gives you the clue of ionization being the link of why it is weak or strong. So next one, the concentration of an acid can be measured in moles per decimeter cubed. Which combination of changes increases the concentration? So the mass of dissolved solid is halved and the volume of solution is halved. If you've reduced the volume, obviously that's going to make the concentration more, but if the mass of the acid is halved as well, that's not really going to increase, that's just going to cancel out and be the same. The mass of the acid dissolved is halved, and the mass of the volume, so the volume of the solution is doubled. That's also going to cancel out. You're half in one and double in the other. The mass of acid dissolved is doubled, and the volume of the solution is halved. Possible. And then the mass of acid dissolved is doubled, and the volume of solution is doubled. So for this last one, we've got double the amount of acid, but we've also doubled the volume, so that kind of cancels it out. So the only one that's going to make sense is that we double the mass of the acid and we reduce the volume by half, because remember, concentration to be high, it's lots and lots of whatever the substance is in a small volume, and then low is much less of that substance within the volume. So we're doubling the amount of substance and we're reducing the volume. That's going to increase the concentration. The concentration of an acid can be determined by titration. So this is that required practical that you've got, where you've got the burette with the volume, measuring an accurate variable volume. The indicator is added to an alkaline flask, indicator telling us the pH, so what number, what colour, if it's an acid, if it's an alkali, etc. Name an indicator that can be used in this titration. So when it says an indicator, it's indicating that we could have multiple answers for this. So give the colour change of the indicator when acid from a burette is added to the alkali in the flask. The one we use most commonly is called phenolphthalein, which you just got to remember. If you spell it slightly wrong but it still sounds correct when you're reading it, you get away with it. Colour changes. In an alkali it is pink, and then it goes to colourless when it's no longer an alkali. Top quality timing, Bell. Then the other indicator that we can use in this practical as an alternative is methyl orange. So this one will start off as yellow in alkali, and then if it becomes neutral or acidic, it will go to orange, red or pink. You could also have litmus paper, which goes from blue to red. And then worst case scenario, if you can't remember any of those, you could put universal indicator, but you can only get a possible of 1 mark for that because it's too quantitative. So the range of colours means it's not going to be an accurate reading of when the neutralisation point is, because you might read one shade of green and someone else might read a different shade. And then the bit underneath, 5.4, sodium carbonate dissolves in water to produce an alkaline solution. Give the formula of the ion, talking about charges, positive, negative, etc., that makes it alkaline. There's only one. The ion associated with alkaline solutions is the hydroxide ion, OH-. So this question looks harder than it is. A student does titration of sodium carbonate solution in nitric acid. The equation for the reaction is as follows. So we've got 25 centimeters cubed of 0.124 mole per decimeter sodium carbonate is neutralized by this much nitric acid. The first thing I've noticed straight away is the unit for the volumes is not the same, which is going to become relevant in a minute. Calculate the concentration of the nitric acid. Give your answer to 3 significant figures. Also, another thing, you're going to do a 5-mark question. One of those marks is going to come from 3 significant figures. So if you see that, you highlight it, you circle it so you don't forget that step at the end. Calculate the concentration. Now the clue in the name, it even says in the question for this one, you should calculate the number of moles of nitric acid, and then the concentration. It even gives you the helping hand of telling you this is how you're going to do it, which is quite kind. So the first thing I would be aware of is the equation for concentration when we're talking about moles and volume. It also kind of tells you that in the question with the unit, because the unit is moles per decimeter cubed. So concentration, our equation for that is moles divided by volume, right? So we're going to use that equation. So first thing is to look at the reaction equation and cross out anything that we don't need. So we're talking about the two reactants neutralizing each other, so all of these are garbage. We don't care about any of those. So I'm going to write those two up at the top over here. So sodium carbonate and 2 nitric acid. Okay. Right, I'll change colour for this. So the thing we're going to need for this is the way, there are many ways of doing this, but the easiest way is to just get out what you've got to start with first. So we've got volume, we've got concentration, we've got moles, and we've got whatever the ratio between the two is, right? So I'm just going to fill in everything that I've got to start off with. So the ratio is obviously 1 to 2. That'll become relevant in a minute. The volumes I've got are 25 centimeters cubed of this one and 23.6 centimeters cubed of this one. The concentration of the sodium hydrogen carbonate is 0.124 moles per decimeter. It's up to you where you choose to do this step, but I would just convert the units straight away. So this unit needs to be in decimeters cubed. So to go from centimeters cubed to decimeters cubed, well, there's 10 centimeters in a decimeter, but because it's cubed, you're going to have to divide it by 1,000 to get it in the correct unit. So the first thing we're going to do is we're going to divide these two units by 1,000. So I'm going to get 0.025 for that one, and I'm going to get 0.0236 for that one. Now the rest of it is pretty easy. Once you've spotted that, that's pretty much the main thing that's going to lose you the marks. So we work out the moles. So to work out moles, all we need to do is we need to do concentration times the volume. So to work out this moles number here, all I'm going to do is I'm going to do 0.124 times the volume that we just got, 0.025, and we get 0.0031. That's our moles. Okay, then what I'm going to do is I'm going to work out the change. So for every 1 mole of sodium carbonate I've got, I'm going to need double that for the nitric acid, so I'm just going to times that mole number by 2. So it's 0.0062 moles. And then we've got our moles, we've got our concentration, our volume, sorry. So we're going to work out the concentration. All we need to do that is what we said before. Concentration is moles divided by volume. So I'm going to do 0.0062 divided by the volume, which I worked out before, which is here, 0.0236. And then the answer I get for that is it's not in 3 significant figures to start, is it? 0.2627 whatever, right? We need to make sure it's in 3 significant figures to get that final mark. This is above 5, so that one's going to round up. So your final answer is 0.263 moles per decimeter cubed. And then obviously that answer goes there. Easy enough. When hydrochloric acid dissolves in water, we've got H plus ions and chloride ions produced. A solution of hydrochloric acid with pH 4 has a concentration of H plus ions of 3.16 times 10 to the minus 5. What's the concentration if the acid is then pH 2.5? The way I would think of this is think about 7 in the pH scale, think about 14, think about 1 to 0. Anytime if we're going towards the acid side, for every number of pH that we decrease it by, we therefore increase the concentration by a factor of 10. So if we went from 7 to pH 6, it would be times 10. If we went from 6 to 5, it would be times 10 again. We're going from 4.5 to 2.5. So that means we're going to go times 10 for 3.5 pH and then times 10 again for 2.5. Overall, you just need it's increasing in concentration by a factor of 100 because it's 10 times 10. So you're just going to do this number times 100 or times 10 twice, and you get 3.16 times 10 to the minus 3. And then which element has atoms that have the same electronic structure as chloride ion? If you can't do this off the top of your head, draw a chloride ion. Chloride ion means it's got a charge. It means it's got a full outer shell, so we can draw the outer we can do the whole thing. So we can do chlorine so that's 10 electrons, 17 electrons, and then that extra one gained. Which element has that same electron structure? But it's got, first off, it's got 8 in its outer shell, so you should know it's got a full outer shell. It should be in group 0. Also, which element has 1 more electron than chlorine does? It's argon. This question is about the use of metals in electrical wires. So we've got 3 metals that the wires could be made of. We've got pictures, and we've got labels. As soon as you see the pictures like this, remember in science, anytime you are given labels, you need to talk about the labels. It's hinting that this is what you should have in your answer, especially if it's a 4 to 6 mark question. You need to be talking about that specifically. Table 5 shows information about them. The higher value, the better the metal is at conducting electricity. So here is our data. We need to be looking at this data and we need to be referencing the picture. So first off, it says evaluate the use of aluminium, copper and silver in the types of wires shown in the pictures. It says evaluate, so that means you're talking about pros, you're talking about the cons. You also need to make a final judgment, your call, right? So first off, we're just going to state all of the obvious things that we can just say from this information, and we'll make a judgment at the end. So first off, we can say is silver is the best conductor. Okay, because it's got the highest conductivity in arbitrary units. We can also say that aluminium is least expensive. And it is also the least dense. Right, I'm just looking at the table. Then I can say something else about it. So we look at copper. So copper is better. Copper is better than aluminium for conducting electricity. But it is not quite as good as silver. However, it is cheaper than silver. Right, all I'm doing is I'm just looking at the table and just writing out anything I can see about this, what the data is telling me. Then we need to talk about, so that's just the data in general. Then we can make some kind of scientific judgments on this. So we've got overhead. If we've got an overhead power cable, then we're going to need cables that are less dense. Right, let's have a look at wiring in homes. So everybody has wiring in homes, so that should be affordable or cheap. So wiring in homes should be cheap. And then if we look at the circuit board, so circuit boards only need, because they're tiny, they only need a small amount of metal. Okay, so we've stated all of the obvious things that we can get from this information. Then we make a judgment. So if we look at all of these, aluminium is best for overhead cables because it's the least dense. We can say copper is best for domestic wiring or wiring in home because it's cheap. And it's a good conductor. And then we've got silver. So silver is best conductor. So it's the best, and it's only needed in small amounts. So it's the best for small circuit boards. There you go. That's everything that you could possibly put. You could probably put less than that and still get 4 marks. All I've done is I've taken all the information given, written everything I could possibly say about all of the metals and what might be needed for each one, and then made a few judgments based on common sense. You could also say at the end as well that copper overall is the best as a compromise between how conductive it is and its cost. Overall, people should use copper in general. Describe how metals conduct electricity. As soon as it says metals and conducting electricity, immediately I'm thinking bonding and structure. Right, this is where we're talking about you've got ionic, you've got covalent, you've got metallic. We don't need to care about the other ones because it's metals, so it's metallic bonding, so it's metal and metal. When we're talking about conducting electricity, this could possibly be, it's going to either be talking about ions, are the ions moving and conducting electricity by carrying a charge, or is it about delocalized electrons? That's obviously not ions, because ions is the one that links to ionic bonding, when that's not what we're talking about. So the first thing we can say is, can metals conduct electricity because they've got a C of delocalized electrons, so therefore they can carry a charge and then this last one, you just got to be careful, through the whole structure. You cannot put throughout, because they've got to go in a specific direction. You can't, that implies that they go in everywhere, all over the place. So you put throughout, it's wrong. You have to put the word through. Electrical wires are usually made of pure metals and not alloys. This is because pure metals are better at electrical conductors. Suggest why alloys do not conduct electricity as well. Remember, for this one, pure metal is when we've got regular nice pattern of atoms that are all the same size. We've got the layers, they can slide, etc. And then alloys is the one where we start placing in different sized atoms that disrupt that pattern. So, answer in terms of structure and bonding, we are still on about metals, but we're on about the size of the atoms in this one because it's alloys. So the first thing we can put for this is, we've got different sized atoms disrupt the layered pattern. So therefore, so that's our first mark. It's two possible marks. So what else can we say? Well, we're on about conducting electricity, so we kind of need to be talking about electrons. Always thinking about electrons when we're on about electricity. Electrons or ions. So electrons, there's a few ways you could put it. You could say have restricted movement. You could have, they don't move through the structure as easily, they don't move around as easily, etc. Something that implies that they're not able to move as easily as they would be if it was a pure metal. This question is about electrolysis. As soon as I see electrolysis, I'm thinking the phrase, don't panic. Positive anode, negative is cathode. Aluminium is manufactured by electrolyzing molten mixture of aluminium oxide and cryolite, which is that classic example that you always get talking about electrolysis. Complete the half equation for the reaction at the negative electrode. Just got to remember that the ions, when they split, they always become discharged at the electrode, so they lose the charge. So with the one on the right, you can imagine there's like a zero, an invisible zero there, because it's got no charge, because it's in its element form, and it's gone from 3 plus to get to that. What did it need to do to get from 3 plus to no charge? It's gained 3 electrons, so you just put a 3 there. Cryolite contains sodium plus ions as well as aluminium 3 plus ions. So just one reason why sodium is not a product of electrolysis. Now this is where your reactivity series comes into it, because it's always the less, so remember you've got most reactive down to the least, and it's always the least reactive element is what will form at the electrode, and the most reactive will always remain in solution. So for this one, you've got sodium plus and aluminium 3 plus. Which one's more reactive? Sodium is more reactive. So sodium more reactive than aluminium. So sodium will remain in solution. student investigated the electrolysis of aqueous solution of a different compound. Aqueous solution is talking about being dissolved in water. So we're going to have some extra ions involved in this. Remember, water is H2O, and the ions that splits into is H plus and OH minus. Hydrogen was produced at the negative electrode and oxygen was produced at the positive electrode. Explain how oxygen was produced at the positive from water for the electrolysis of this aqueous solution. So during this, we're looking at the positive electrode. What is going to go to the positive electrode? It's the OH minus ions, because obviously opposites attract. So the first thing we can say is water will break down into H plus and OH minus ions. Because we're in aqueous solution, so we've got two extra ions, and then so that's 2 marks right there, talking about the ions. And then we need to say where the OH minus ions will go. Opposites attract, so if they're negative, they'll go to the positive electrode. So OH minus ions are attracted to positive electrode. Okay, and then we're going to talk about where does the oxygen come from. So when they go to the electrode, they will be discharged, and we end up with oxygen and water forming. So they're discharged. Also, could say they are oxidized to form oxygen and water. So a student compared the volume of 2 gases collected. How can the student change the apparatus in figure 7, which is over here, to compare the volumes of the 2 gases produced more accurately? Give one reason. So the main thing to spot for this setup, which is if we're on about volumes and measuring, they've got it set up with test tubes, which you don't use to measure volume because you've got no idea what the measurement is. So you need to think of a more suitable piece of equipment that you could replace them with, that you would be able to measure the volume of the gas being produced. Most obvious one is use a measuring cylinder. Instead of the test tube. Why? Because it has a scale on it, it has the lines. Or you can say it's used to measure volume. Next one, the overall equation for the reaction is 2 waters makes 2 hydrogens and 1 oxygen, 1 mole of oxygen. So what is the volume of oxygen produced when 20 centimeters cubed of hydrogen has been produced? You need to look at the products and look for every 2 mole of oxygen that we only get 1 mole of. For every 2 moles of hydrogen, we get 1 mole of oxygen made. So that tells you that whatever the volume of hydrogen that has been produced, you'll always get half of that volume in oxygen. So the answer is half of 20, which is 10. This question is about elements in the periodic table. Argon has the atomic number 18. Explain why argon does not form compounds. So compounds, remember, is different elements that are chemically combined. So getting a reaction to make something new. Answer in terms of electrons. You need to talk about electrons in your answer. You should hopefully know that argon is a noble gas. So that means it's in group 0, which tells us, if you draw, you could draw all the electron structure for it as well if you want to prove the point, but argon has a full outer shell of electrons. Or you could say it has a stable arrangement of electrons. Either one. That's 1 mark. So therefore, what can it not do? If it's forming a compound, it means it's a chemical reaction. Think about what happens in terms of chemical reactions. It means it cannot share or transfer electrons. Or you could say gain and lose electrons and share electrons, etc. That's how you get the 2nd mark. Phosphorus is the element below nitrogen in the periodic table. Nitrogen, first off, I'm thinking is in group 5. so it's going to be similar. Predict the formula of the compound formed between phosphorus and nitrogen. It gives you the clue. It's in the same group as nitrogen, and you may have seen this one before where you have nitrogen, it's got 5 electrons, it needs to gain 3 to get a full shell, and hydrogen only needs to gain 1. So you're going to end up with 3 hydrogens around it, like that. And then those 2 extra ones on nitrogen, that's ammonia. You would assume it's in the same group, so it would react in exactly the same way. The formula for that is NH3. The formula for phosphorus reacting with hydrogen would be PH3. Next one. The tellurium is the element of the periodic table with atomic number 52. Predict whether tellurium reacts with metals. So there's a few ways you could say for this. I'll split it down the middle because there's reasons why you could say yes, there's reasons why you could say no. So the first thing you could say is, so there's 2 possible marks for this. You need to say something and then say because. So, or therefore, whatever. So first thing we can say is it's on the right. So you can say yes because it's on the right, so it's a non-metal which react with metals. You could also say it's in the same group as oxygen and sulfur, so will react in similar way. Now there's reasons why you could say no. So you could say it's near the bottom of the periodic table, so it is a metal. Or you could say it's near the bottom left, so we actually don't know if it's a metal or a non-metal. So either way, you say yes and you give a reason where it is in the periodic table, what does it tell you, or you say no. There are a few answers you could put for that. Barium is an element of group 2 of the periodic table. Hint, if it says on about barium reacting with hydrochloric acid, it means it's going to react in a similar way to magnesium, to calcium, etc. So just 2 observations that could be made when barium reacts with hydrochloric acid. You could pretty much just imagine that it's magnesium and it's just going to be a more reactive version of magnesium. So you can say if you put it in the acid it will fizz. You could put it in the acid, it will say, you could say the barium would disappear. You could say it forms a colourless solution, as magnesium does. You could also say increase in temperature. All I've done is imagined it's magnesium, replace the word magnesium with barium, same thing. Right, a balanced symbol equation for the reaction between barium and hydrochloric acid. So first off we can start off with barium, which is Ba, and hydrochloric acid. Same as before, I'm imagining that it's magnesium because it's going to follow the same trend because it's in the same group. So the formula for magnesium chloride is MgCl2 because you need 2 chlorines to cancel out the magnesium ion charge. The same would be for barium chloride. Plus, and then if it's just a metal and an acid, then we get hydrogen. Then I just need to balance it. The bariums are currently balanced because there's 1 and 1. There is only 1 chlorine and 1 hydrogen on this side, whereas there is actually 2 on this side. So we can try doubling. It's just a trial and error game, this. So you double the HCl's and see what happens. Now we've got 2H, 2Cl, 2Cl, 2H, 1 barium, 1 barium. Done. This question is about displacement reactions. So straight away when it says that, I'm thinking about reactivity series. I'm thinking about displacing a less reactive element with a more reactive one in the compound. So iron is extracted from iron oxide with a displacement reaction with carbon, obviously yeah, because carbon's more reactive than iron. Which substance in the equation is reduced? So straight away thinking about oil rig. I don't know if this will be relevant yet, but we'll see. Then give one reason for your answer, and then it says here, crucial point, answer in terms of oxygen. So you've got to be careful here because this oil rig is on about movement of electrons. So obviously oxidation is loss, reduction is gain of electrons. If we're talking about oxygen, the first initial reasoning behind the words oxidation and reduction was movement of oxygen. So think about which one is on about the loss and gain of oxygen. Obviously the one that's on about gaining oxygen is the one that sounds like oxygen. That's oxidation. So reduction is loss of oxygen. So this means lost oxygen. Now we need to figure out in this which one has lost oxygen. To start with, this one has oxygen on it and then it doesn't anymore. So the element that lost it was iron. And then just put your reason in terms of oxygen is it lost oxygen. Which expression shows how to calculate the mass of carbon needed to produce 1 mole of iron from iron oxide? In this question, it gives you the relative atomic mass of carbon. It's a bit like a moles question, so we're looking at what mass of carbon is needed to make a certain amount of iron. We don't care about the iron oxide, we don't care about the carbon monoxide. We are given that we have 1 mole of this, and we need to work out what the mass of this is that we need. Remember, it's a bit like a simple moles question, so if you remember the equation, mass equals Mr. moles. So mass is molecular mass times moles. So we're going to have to work out what the moles of this is and then times it by the mass. So the main thing for this to get this right is you've got to figure out how do I do the ratio of 2 ions. I need 3 carbons. How do I go from the 2 ions to the 3 carbons? To do that, I'm going to divide by 2 and then times by 3. What's the fraction that's the same as doing that? It's 3 over 2. There's only one that actually does that, and it's that one. So student investigated displacement reactions A, B, C and D. In the table shows you what reactions are taking place. There's the method. It's not really relevant for this first bit. The ionic equation for reaction 1 is A plus 2B plus makes 2B plus A2 plus. Why is this a redox reaction? So redox, remember you're thinking of oil rig again. Redox reaction means it's got both reduction and oxidation in it at the same time, which is pretty much every reaction ever. So we need to figure out which one represents what's happening in this. It's not going to be the bottom two because they're both gaining or losing. It's on about losing and gaining at the same time because we've got oxidation and reduction. Remember, oxidation is loss, reduction is gain. So then we need to figure out which one is gaining the electrons and which one is losing the electrons. So how does A go from A with no charge to A with 2 plus charge? It has to lose electrons. And then how does B go from a plus charge to no charge? B is gaining electrons. So it's A loses electrons, B plus gains electrons. 9.4. Which of the 4 metals has the greatest tendency to form positive ions? Use table 6. So we're looking at this table. So we need to figure out, it's about displacement reactions, so it's about reactivity series. Talking about reactivity, remember that the more reactive element will displace the less reactive one in a salt. So for this first one, we've got a reaction taking place, so that tells you that A is more reactive than B because metal A has displaced B to form something new. In this one we've got a reaction, so it tells us that C is more reactive than A. So far C is the most reactive one because it's the highest up the list. Then the bottom one, nothing happened. So that tells us that C is less reactive than D. So C is more reactive than all the other ones, but it's not as reactive as D. That tells us that D is the most reactive, so it's going to have the greatest tendency to form an ion because it's the most likely to react. So the answer is D. Nitrate ions form the formula NaNO3-, which is a helpful, useful bit of information for this question. Which of the 4 metals could be aluminium? First off, you should hopefully know that because of aluminium being in group 3, aluminium makes 3+ ions. So we need to look at which one of these. So easiest way to think of this is if you have an aluminium 3+, you're going to need 3 nitrates to cancel that out. So we look at this and we find which one of these has got 3 nitrates attached to it. It's this one here. So the answer is C, because aluminium forms 3+ ions, so therefore 3 nitrate ions needed for 1 aluminium. So metal X is extracted from an oxide of metal X by reacting with hydrogen. Here's the equation. Percentage atom economy for obtaining the metal X in this method is 77.3%. Calculate the relative atomic mass of X, and we're given the masses of hydrogen and oxygen there. We're on about percentage atom economy, so first off we're going to need to remember what is the equation for that. So I'm going to write that down. Percentage atom economy is your mass of useful product divided by mass of all products, and it's percentage times 100. So in this one it's a little bit different because we are not working out percentage atom economy in this, we are working out what X is, what the mass of X is. We're given the atom economy. So all I'm going to do is I'm going to sub in what I know into that equation there, and then I'll see if I can rearrange it to find X. So first off, our percentage atom economy in this question is 77.3%, equals mass of our useful products is whatever the mass of X is. We don't know what it is because that's our useful product. So it's going to be X divided by whatever the mass of all of the products is, which is going to be X and waters added together. So X plus whatever 3 waters is. Quick working out. Hydrogen's 1 each, which is 2, plus 16 is 18, but there's 3 of them. So the mass of 3 waters is 54. So X plus 54 times 100. Now at this point, it's not even science anymore, it's just algebra, maths. So we do this bit by bit. There are a million ways to do this. It's up to you. If you're good at maths, you can do different ways. So I'm going to get rid of the 100 first. So I'm going to divide both sides by 100, and then I'll rewrite it again. So 77.3 divided by 100 is 0.773 equals X over X plus 54. That's 100 gone. Then we're going to get that X plus 54 from the underneath of the brackets, so we're going to times both sides by X plus 54. So if I rewrite that out, I'm going to have 0.773 times X plus 54 is X. Then I am going to expand, I'll expand those brackets next. So that's going to be 0.773x plus whatever 0.773 times 54 is, which is 41.742 equals X. Then we're going to get the X's onto one side, so we're going to take away 0.773x from both sides. So, and obviously that's just 1x, isn't it? So 1 take away 0.773. So that gives us 41.742 equals 0.227x. Then to work out what x is on its own, I'm just going to get rid of this from this side. So I'm going to divide both sides by 0.227, which gives us, so whatever 41.742 divided by 0.227 is, so the answer is x is 184. You get, it's 183.885 or whatever it is, but you just round it to a whole number, is fine. The question is about titanium dioxide. Self-cleaning windows are coated with a layer of nanoparticles of titanium dioxide. Nanoparticles, you're thinking large surface area for volume. Titanium helps sunlight. Titanium dioxide helps sunlight break down dirt particles, attracts water so dirt is washed away by rain. It's used instead of fine particles for fine coating of self-cleaning windows. Suggest why. First off, it's nanoparticles, so the first thing you can obviously say is large surface area to volume ratio. That's kind of the main reason why we use anything that's small in terms of rates of reaction, nanoparticle coatings, etc. And then another reason why, so you could do two things. What's the reason why? If it has a large surface area to volume ratio, you can have less substance needed to have effect. You could also put it lets sunlight through, lets more light through, because there's less of it. Titanium is extracted from titanium dioxide in a two-stage process. The first stage is in this equation. Calculate the volume of chlorine gas needed to completely react with 100 kilograms of titanium dioxide. We're given the relative masses of oxygen and titanium. We're given the volume of 1 mole of gas. It's giving you a hint that we're going to have to work out moles. The equation for moles is mass equals Mr. moles. Or if we want to work out moles, you do mass over mR. The other equation we're going to need, because we're on about volume of gas of chlorine, the way you would work that out is volume of gas is moles times 24. You would get your answer in 24 in decimeters cubed. So first off, we're talking about titanium dioxide reacting with chlorine. So these lot are irrelevant. I'm going to write the other ones that we actually care about here, including the big mole number. Next, we write down what things we've got. So we're on about, we need mass, we might need mR, need moles, need ratio. Then we're going to fill in what information we've got already. So we've got mass of titanium dioxide is 100,000 grams, because it's 100 kilograms, right? To go to grams, you times 1,000. Then we've got the mR of titanium dioxide. Titanium is 48, 2 oxygens is 32, that gives us 80, so the mR is 80. Then we're going to work out, we can write down the ratio. So the ratio is 1 titanium dioxide to 2 chlorines. So for every 1 mole of titanium dioxide, we need 2 moles of chlorine to fully react. We work out the moles of titanium dioxide. That's, as mentioned before, to work out moles, we do mass over mR. So that's going to be 100,000 divided by 80, which gives us 1250. Then we need to work out how many moles of chlorine there are. We already said the ratio is 1 to 2, so we're going to times this number by 2 to get the correct number of moles of chlorine. We do not need mass of chlorine because that's not what we're working out. We're working out the volume of gas. If you remember earlier, I told you the volume of gas is moles times 24. So all we've got to do to get the volume of chlorine needed, we're going to times this number by 24. 2,500 times 24 is 60,000. Your answer is in decimeters.